Dun 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 dun. Do 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 do. Okay, that's enough. Welcome to Friday marking. Yay! It's my favorite time of the day. We're gonna mark our work today, and then I'll have maybe a little something for you to work on afterwards. 2 sections of the video today. So if you're in year 3, you're up first. You guys are going to be over here. And if you're in years 4 to 6, you're going to be over here. Your work 4 to 6 is pretty much the same. It's really just about the workload, what I asked you to get through, as opposed to maybe the content of what you're doing, at least at this stage. Today anyways. So I'll give you timestamps below, and you can just click the timestamp to jump to the right part of the video so you don't have to watch things that do not pertain to you, unless you really want to. I don't know why you would, but maybe you want to. Okay, let's get started. Year 3. I can't really mark the drills, and part of the goal of this whole part of your maths this week was sort of as a, where's my pen? As an offline activity. And what I mean by that, it was something for you to do. You didn't need the iPad in front of you, right? So when you create a set of flashcards, you literally just cut out a square of paper, right? And on the front of the paper, you put the equation, so like 1 plus 2 plus 3 plus 4 plus 5. And on the back, you put the answer, which is 15, right? So here's the front, here's the back. And you make a stack of these, and then you shuffle them and you quiz yourself. Now, correction, Abby Abris, who is a legend, noticed that I made a mistake here. So if you think about it, 1 plus 9 is clearly 10, and 3 plus 7 is 10, and 5 is not 15, but 25. It's a weird 2, Mr. Black. Hang on. Is 25. So my nice little theory about all of these being close to 15 or 31 is a little bit out of whack, but I'm not going to let something like a tiny mistake bother me. Okay, so anyways, just wanted to note that as well. And thank you, Abby. Abby gets an extra 200 points added to her final score at Mount Sinai College. You know when you graduate, you get a final score? Yeah. Well, Abby gets an extra 200 points. I'm just kidding. There's no final score. Could you imagine if there would be? Okay. Yes, so I'm not going to mark the drills. There's really no way for me to do that. I'm just trusting that you guys did the work. In the future, I'm going to have a lot more activities like this, so you'll get used to them. Okay, let's go over here to the quick 6. Let's mark the quick 6. Hang on a second. Okay, question number 1 is, what is the sum of the sides of a regular hexagon whose side length is 3? So the clue here was regular hexagon. See if I can draw one. I've always found freehand drawing regular shapes, as in side lengths being equal, is really tricky. Bit wobbly. Okay, well, there you go. If it's regular, it means all sides are equal, or congruent is the word that we use. And if one side is 3, all sides are 3. If a hexagon has 6 sides, then I use the operation of multiplication, and I get 18 is my answer. How many times does the number 5 appear in the digits 1 to 50? Okay, for this problem, I like to work systematically. So you can see I've sort of made a list of numbers here. These are the numbers of 1 to 10. These are 11 to 20, so on and so forth, down to 50, my final number. How many times does the number 5 appear? Well, one of the ways I could solve this is just by counting them in each of these sets and then summing them. So 5 will appear in 1 to 10 only once, the number 5. 5 will appear in 11 to 20 only once, in the number 15. 5 will appear in 21 to 30 only once, in the number 25. 5 will appear in 31 to 40 only once, in the number 35. And 5 will appear in 41 to 50 twice, one for 45, and then obviously the 5 in the 50. So if I sum these, 2 plus 1 plus 1 is 4, plus 1 is 5, is 6. So the number 5 appears 6 times. Next one, I have 3 hats, 2 shirts, 2 shorts, and 1 pair of shoes. How many unique outfits do I have? Okay, here's a model representing the question. You can see there's 3 hats here at the top, right? There's 2 shirts and 1 pair of shoes. One way to solve this is drawing lines. You could draw a line from a hat to a shirt to start an outfit, and then from the shirt to the shoes, that's 1 outfit. Then you could draw a hat to this shirt, and then to the shoes, that's 2 outfits. And then same with this, it's 3 outfits, it's 4 outfits, 5 outfits, and 6 outfits. That's already pretty confusing just looking at the lines, and we have a very small amount of items. What's an easier way to do this? Well, we could use multiplication. The rule of how things combine in this way is that the sets are multiplied. So I said that the answer was 6. We can also arrive there by saying 3 hats times 2 shirts times 1 pair of shoes is 6 combinations. A standard piano has 88 keys. 36 of them are Mr. Black. What a good joke. How many of them are Mr. White? This is just a subtraction problem. If I've got 88 keys in total and 36 of them are black, the remainder will be white. 8 minus, because there's no other color keys. There's no pink keys in a piano unless you have a paintbrush and you paint your piano pink. Don't know why you do that. Actually, it could be pretty cool. Anyways, 8 minus 6 is 2, and 8 minus 3 is 5. So 52 of them are white. Okay, I did have a few questions about this one, and I should have been clear. I just wanted you to give me the answer with a remainder. I hope no one tried to convert these into decimal form, but if you did, I'm curious to see your answers. 42 divided by 5. Straight away, you should know that 42 is not evenly divisible by 5. Okay, 5 will go into 42 8 times, and I can prove that because 8 times 5 is 40. However, 42 is 2 more than 8 times 5. Therefore, I have 2 left over. 8 remainder 2. And same follows for here. Okay, so how many times will 12 go into 56? Well, this is where my 12 times tables is handy, right? So, for example, 12 times 4 is 48, and 12 times 5 is 60. Well, 60 is too much, so clearly 12 will go into 56 4 times, 4, with some left over. And the leftover amount is the difference between 48 and 56, which is 8. So 4, remainder 8. If that was very tricky or you felt that was really over your head, don't worry. We'll get there. That's a pretty tricky concept to teach you with a screen. It's really nice to actually use physical objects. Okay, there's your first quick 6. Number 2. Change from $10 for an item that costs $6.40. Here's how I like to do this. I put the 2 numbers on opposite ends of a number line. So I gave $6.40 to the clerk, and she gave. So I gave the clerk $10, and the item cost $6.40. So how much change do I need? Sometimes I solve this with a number line. So if I add 60 cents to $6.40, so plus 60 cents, okay, that hops me up to $7 exactly. And then if I add $3, so plus $3 to 7, that hops me up to 10. Therefore, if I combine these hops, I get $3.60, which is the difference. This is the change, right? If I add $3.60 to $6.40, I get $10. Okay, this is sort of the same question as before, but with the trick thrown in, right? So the first set of 10 digits only has 1 3 appear in it, the number 3. Same pattern as before. This one just has 1 for the number 13. This one has 2 because you get 23 and you get 30. Okay, but now it gets a little bit trickier. I'll show you why. Let's list all the numbers from 31 to 40. 31, 32, 33, 34, 35, 36, 37, 38, 39, and 40. Okay. How many threes appear in this series? A lot. 1, 2, 3, 4. 5, 6, 7, 8, 9, 10. So this set has 10 threes. So now we have to sum these numbers. 10 plus 2 is 12, plus 2 is 14. So the answer is you get 14 appearances. Much bigger than that previous one. Cool. And the last one is just a bit of drill. Okay, 10 times 5 is 50. Therefore, 10 times 50 is 500. And 10 times 500 is 5,000. Okay, if you're not sure how I did that so quickly, I know that 50 is 10 more than 5. So my answer of 50 needs an extra 0. It needs to be 10 times bigger. And I know that 500 is 10 times more than 50. Therefore, my answer has to be 10 times bigger than 500, which is 5,000. So you can see how the zeros increase here, right? And, of course, the zeros increase here. And then what's interesting is let's say I then went even crazier, and I did 100. I increased a 0 here times 5,000 and increased a 0 here. Well, now my answer needs to include a double increase. Okay, the extra 0 from the 500 increase, but also the extra 0 from the 100 increase. What number is that? It's 500,000. So I've jumped up 100 times bigger than 5,000. Very cool stuff. This is a triangular prism. It's drawn to look 3D. The dotted lines are supposed to be the interior that you cannot see, and the vertices are countable. 1, 2, 3, 4, 5, 6. That's the answer. Next one. I'm thinking of a 3-digit number with an odd number in the hundreds, an even number in the tens, and an odd number in the units. So odd, even, odd. It is less than 370 but greater than 350. What are my options? Well, here are my place values. So we got the hundreds, the tens, and the units. And we know that hundreds has to be odd, tens has to be even, and units has to be odd. And we know the range. Okay, it has to be less than 370 but greater than 350. Okay, well, if it can't be bigger than 370 and it has to have an odd number of the hundreds. The only option for hundreds is really just a 3, right? Because the next odd number is 5, but that's bigger than 370, so that doesn't work. If it has to have an even number in the tens, well, the even number options that I have are 2, 4, 6, or 8. And it has to have an odd number in the units. So the options I have for odd number of units are 1, 3, 5, 7, and 9. I could include 0 here. Okay, so then how do we find what our options are? Well, we just need to look at the final constraint, right? It has to be, or the two constraints, has to be greater than 350 or smaller than 370. So if I made some numbers from here, like for example, if I made like 301, that doesn't work because that is less than 350. I could make, in fact, anything with 30 all the way up to 309 would not work. So those are out. What about 32 something? No, those don't work because those are still less than 350. So as you can see, I have to start at the first even number, which is bigger than 350, which is 3 and a 6. And then I can put any of those odd numbers in there that I want to. So some possibilities would be 361, 363, 365, 367, 369. And then I could try to consider the next set, which is a 3 with an 8 there, but of course that's already bigger than 370. So these are my options, and there are 5 of them, 5 possibilities. Great. Okay, the next one is a very similar question to the other two that we've had. I've got 3 types of pasta times 3 types of cheese times 3 toppings. Now, Tamer rightfully asked me if this was a trick question. I guess what I meant by types of topping was it could be like roasted zucchini or roasted pumpkin or maybe chopped cherry tomatoes or parsley. Who knows? Anyways, 3 times 3 times 3 is 27. You could also express this as 3 to the 3rd power, which is 27. Cool. A flute has 16 keys. How many keys does a duo of flutes have? You have to know what the word duo means. It means 2. So 2 flutes, 16 times 2, which equals, of course, 32. Okay. And the last one, no mystery here, 107, 152, and 602. Just sort of interesting to note, I guess, how where the 5 is moved in the place values with the addition operation really creates not much of a pattern, right? Because different things are happening. 5 gets added to the 2, 5 gets taken the place of the 0, and then the 5 gets added to the 1. So unlike our multiplication where we really see a pattern growing when these go up, increase by sizes of 10, addition doesn't really work that way. Addition's moving a lot slower, right? Adding something that's 100 times bigger, okay, is only going to give us 500 more from our 102. Anywho, just thought that was interesting. Okay, you 3, if you're still watching this, I want you to take a break, go stretch your legs, get a drink of water, come back, and we'll mark these last 3 questions, and then you're done. Yay! Okay, I'll read this to you. Find a whole number which is less than 100, a multiple of 3, a multiple of 5, it's odd, and such that the sums of the digits are odd. Okay, the answer that I got to this problem, oh, hang on. Yeah, okay, we're working. It was 45. And I'll show you why. So, is 45 a whole number? Yes, tick. It's not a fraction. Is it less than 100? Yes. Oops. Yes. Is it a multiple of 3? Yes. How can I know that? Well, one of the ways to know if a number is a multiple of 3 is a few ways, but a nice fast way is sum the digits. And if that number is evenly divisible by 3, which it is, 9 divided by 3 is 3, then the whole number is divisible by 3. So that's pretty nice. A multiple of 5. Yes, 45 is a multiple of 5, and I can prove that because I know that 5 times 9 is 45. And such that the sum of the digits is odd. Well, I kind of already proved that back here when I said that 4 plus 5 is 9. Great. Okay, this is one of my favorite questions, and big shout out to Noah Stern, because she was the first person to send me some work for this, and she nailed it. It was great. Really good working out. One of the words you don't know or might not have known is congruent. And congruent comes up a lot, and it literally just means equal. Equal to, I suppose. Equal to what? Equal to itself, right? The sides are equal to each other, therefore this object is made up of squares. Okay, we only know one thing about it. Well, we know two things. We know that it's congruent squares. We know there's 5 of them. And I guess the third thing we know is that the perimeter is 72. So that means that if I sum the length of this side, 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 and this side, I get 72. So I need to find the area of this whole figure. That's what it's asking me. In order to do that, I need to know the value of at least one of these sides. Well, to get there, I'm going to use the fact that the perimeter of 72 is made up of a sum of 12 sides. How do I know there's 12? Let's count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Therefore, if I divide 72 by 12, I will have the side length of one of these squares. 72 divided by 12 is 6. So the side length of one of these squares is 6. Okay, next step. How do you calculate the area of a square? You multiply its length times its width. So if I said L for length and W for width, I could write a formula that says A for area equals L, length, times width. Now both of these L's and W's are the same number. They're both 6. So the area of this square here is 36. Therefore, the area of this one is 36, and this one is 36, and this one is 36, and this one is 36. Whoa. So I need to sum up 5 36s, and I can use multiplication to speed that up. 36 times 5. You with me? Okay, so 6 times 5. Sorry, I need to go. 6 times 5 is 30. 5 times 3 is 15. Hang on. It's 15, and 15 plus 3 is 18. So I get 180. And that is my answer. 180. I wanted to say something else about this, but can't remember what it was. Oh, maybe you don't know how to multiply like that, and that's fine. You could just multiply like this. Okay, you could say 30 times 5, and then 6 times 5. You could break the 36 apart. Put the 30 here and the 6 over here. Okay, 30 times 5 is 150. And I know that because I know 3 times 5 is 15. Therefore, 30 times 5 is 150. 6 times 5 is 30. Oops. 30. And then I can just sum these. 0 plus 0 is 0. 5 plus 3 is 8. 1 plus 0 is 1. And you'll get the same answer. So don't, if this algorithm was crazy to you, don't worry about it. Just split them off in the partial product method. All right. Now, I love this problem because there's an easy way and a hard way to do this problem. There's a brute force way, and there's an elegant solution. The brute force way to solve this, brute force, is to literally just do the operation. Sum that, plus that, plus that, take away that, take away that, take away that. But why would you do that? There's a much, much easier way to solve this, and I'll show you right now. If you took a moment to actually look at these numbers, you may have noticed that this number is 100 less than this number. So 100 less. Okay. Then you might have noticed that this number is 100 less than this number. And of course, this number is 100 less than this number. So what that means is that if I summed up all of these, I'd have some number. We'll call it, I don't know, n. And if I summed up all of these, I would have another number. I don't know, we'll call it x. No matter what these are, x is going to be 300 less than n. So when I subtract them, I'm going to be left with just 300. That's the answer to the question. Now, you could have done all of the brute force calculations, but there's a much easier way to solve these kinds of problems. You have to look for a pattern. Look for. And then you have to apply a little bit of knowledge about what you might know about operations. Okay. Thank you, Year 3. That's a 25-minute video. I think that's enough for today. And I will see you when I see you. Bye. Hello, Years 4 to 6. Your work was pretty similar this week. Just really changed the volume. So let's get going. I won't mark any of the drills. I just assumed that you had made those flashcards and worked on those. I've got a couple of creative ideas how we might be able to do this in the future, but for this week, give yourself a tick for the drills. Okay, quick 6. Let's go. Number 1, sum of the sides of a cube is length is 3 is 36. How many times does the number 5 appear in the digits 1 to 60? Well, it appears 16 times. And if you don't believe me, I made a little chart here. So we've got the numbers 1 through 10, you have the number 5. And 11 through 20, you have 15. 21 through 30, you've got the number 25. These are each appearances of 5, right? Okay, and 31 to 40, you have 35. And 41 to 50, you've got 2 of them. You've got 45 and 50 itself. And then in 51 to 60, you've got 1, 2, 3, 4, 5, 6. Tricky. 7, 8, 9, 10. So 10 there, plus 2 is 12, plus 2 is 14, plus 2 is 16. Next one is literally just a very simple combinatorics problem, right? 4 hats, 3 shirts, 3 shorts, 2 pairs of shoes. 4 times 3 times 3 times 2 is 72. Standard piano has 88 keys, 36 of them are Mr. Black. Funny joke. How many of them are Mr. White? 56 keys. I shouldn't need to explain how to do that one. I use subtraction. You could use addition if you wanted to. 102 divided by 5. 5 goes into 120 times with 2 left over. 102, that is. And then the same holds true here. So if I divide 1020 by 50, both of these have increased by a power of 10, a factor of 10, not a power of 10, a factor of 10, then that means that your division won't change. Okay, you're sort of locked in place here. There's still 20 50s with 2 left over to go into this number. So it's a nice little trick for division. If you ever get stuck on these bigger problems and you notice that you can just make them simpler, like that, get rid of the 0, and you realize you've got a simple problem up here that you can solve. Okay. Quick 6, number 2, $3.60 for that change. I shouldn't need to show you how to do that. How many times does the number 3 appear in the digits 1 to 40? It appears 14 times with the same strategy as used above. So if you're not sure how I got this one, go look at the answer again for the one above. My phone comes in 4 colors. So 4 colors is here, 2 different sizes of memory, and 3 types of cases is 4 times 2 times 3, which is 24. A standard guitar has 6 strings and 22 frets. How many notes can it play? You may have been a bit hung up on this part. The idea is that 1 fret equals 1 note, even though that's not necessarily true for the purposes of this question. So it becomes 6 times 22, which is 132. You could solve that with algorithm, or just I did the partial product method here. Got the same answer. And then down here, just another one of those types of problems about scaling. So 102 times 5 is 510. 102 times 50 is 5,100. And 102 times 500 is 51,000. Beautiful. How many vertices do 2 triangular prisms have? Here are 2 triangular prisms. I'll count the vertices on 1. There's 6 of them. So therefore there must be 12 in total. To find the digital root, this is sort of like a property that all numbers have. For example, a number can be a square number, right? It can be an odd number. You can also calculate its digital root. Simply sum the numbers of each place value. For example, the digital root of 53 is 5 plus 3, which is 8. However, if an answer flows over to the tens column, you just keep summing. So the example I gave is 99, because 9 plus 9 is 18. So you're not done yet. You need to do 8 plus 1, which is 9. And now you can stop. 9 is the digital root of that number. So the answer is, question is, what is the digital root of 555? I did it up here. So 555 breaks down to 5 plus 5 plus 5, which is 15. And then 15 breaks down to 1 plus 5, which is 6. So the digital root of 555 is 6. Another one of these types of combination problems. I've been giving you these for a reason. You'll see later there's an Olympiad problem that sort of builds upon this concept. So I have 3 types of pasta, 3 types of cheese, 3 types of toppings. Tamer commented to me that Mr. Black, cheese is a topping. So yes, he's correct. Thank you, Tamer. But I was thinking toppings like roast zucchini or something. So anywho, it's 27. A flute has 16 keys. How many keys does a quartet have? You should know that quartet means 4. Quarter is kind of hiding around in there, right? 4. 16 times 4 is 64, which you should know anyways, because 64 is one of your powers of 2 numbers, 2 raised to the x, and those are nice to memorize. Just wanted to demonstrate here how adding and increasing powers of 10 doesn't really scale your answer accordingly, as you might expect from multiplication. So 102 plus 5 is 107. 102 plus 50 is 152, and 102 plus 500 is 602. Clearly 602 is a lot bigger than 107, but you don't have this massive growth factor where you're looking at an answer that is like 10,000 times bigger, as you did when you were up here with multiplication. Okay, so it's just something nice to keep in mind when you see multiplication. You're talking about big steps, big increases, especially when you do powers of 10. Okay. All right, it's Olympiad time. First one. You could have brute forced this one just by straight up solving it. However, I wouldn't do that. I would just pause for a minute and look for a pattern. So I'm just going to write down look for a pattern. Look for a pattern. I've got the answer over here, which is 300. The way I solved this was I noticed that this number is 100 less than this one. And this number is 100 less than this one. And this number is 100 less than this one, okay? So if this is the side that you're summing, and this is the side that you're subtracting, and the only difference is that the subtraction side is 300 less, then that means that this side, the only difference is that it's 300 more. Therefore, what you're going to have left over is literally just 300. Because if these sides were equal, well, you would have 0 left over. But you don't. This is 300 more. So you have 0 plus 300, really, is one way to think about it. You've got 300 left over. Okay. This next one I thought was pretty easy, so maybe I missed something, and if I did, leave a note in the comments. But I've got 8 boxes here, and it says they can contain at least one marble, so no 0 marble set. Each box contains a different number except for 2 boxes which contain the same number of marbles. What is the fewest? So I am maximizing fewest. I'm trying to find the least. And if I'm going to only be allowed one double, right? 2 boxes that contain the same number, then I should double the smallest number, which is what I've done here. So I've put a 1 here and a 1 here in this box. And then I gave myself the next smallest number, which I could, which is 2. And then just went up the way like that, like 3, and then 4. Give myself 5, then 6, and then, of course, 7. And then the question is, so what is the fewest number of marbles you could possibly have given those circumstances? And I got 29. If I'm missing something, because this just seems so easy, so if I'm missing something, please let me know. I do make mistakes, like, all the time. Okay. Find the whole number, which is less than 100, a multiple of 3, a multiple of 5, it's odd, and the sum of the digits is odd. I just used guess and check and got to 45. I don't know if there are other answers. Guess and check, there might be, but I'll show you 45 does meet the requirements. It's less than 100, tick. 45 is a multiple of 3. 3 goes in there 15 times. It's a multiple of 5. 5 goes in there 9 times. It is an odd number because it ends in a 5. And if I sum the digits, in other words, I find the digital root, it's 9, which is odd. We have a winner. Okay, this problem is bananas. And, okay. I don't know if you read my comments when you tried to solve this one, but it took me a long time to figure this problem out. And this was years ago. I did this. And I had to have Mrs. Weiss help me, and then she didn't understand. And then I had a revelation driving to work. Actually, driving to you. Because I work at school. I am a teacher. Okay, if you first read this problem, you will fall into a trap, and here's why. Let's read it together. Okay. Takeru, Japanese, has 4 1 centimeter blocks, 3 5 centimeter blocks, and 3 25 centimeter blocks. By joining these blocks to make different total lengths, how many different lengths of at least 1 centimeter can Takeru make? Okay. Up to this point, just like the problems I've been giving you, you probably thought that this was a simple combinatorics problem. I have 4 of one thing, I have 3 of another thing, and I have 3 of another thing. Well, that's easy, Mr. Black, you said. 4 times 3 is 12, and 12 times 3 is 36. So there are 36 combinations. Well, unfortunately, that is wrong. And the reason that's wrong is because if you think about what it's asking, it says to make different total lengths. So I could have a length that is literally just 1 centimeter and 5 centimeters. A length that doesn't include a 25 centimeter block at all. Well, that's allowed by this problem. So let's just take a step back and see what that really implies by what we're saying when we treat this like a simple combinatorics problem. Okay, here's a simple combination problem that you would all solve. Let's say you have 4 hats, you have 3 shirts, and you have 2 pairs of shoes. I know those are my shoes. They look terrible. 3 pairs of shoes. Those are my shoes. You all know how to solve this. You say, this is easy, Mr. Black. It says 4 times 3 times 3, and you're correct. It is. So how is this problem, why is this problem different than the other one? Well, the reason is actually very, very subtle. When you're given this problem, it is implied that you are making a whole outfit. You're not going to leave the house without a shirt on, right? Or you're not going to leave the house without your shoes. So you are not considering what's called the empty set. Because if you think about it, there you have more than 3 shirts. You also have, really, in a way, a 4th choice for shirts, which is to not wear a shirt at all. That's a 4th choice that you have. Literally wearing no shirt. It's a 4th choice. Now, we never consider this choice because these kinds of questions assume that we want the whole outfit. So that logic also holds. You have a choice not to wear a hat. That's another option to put into the mix, not hat. And you have a choice to not wear shoes, no shoes. So if we allowed for you to have incomplete outfits, I'm going to write that over here. What on earth? Incomplete outfits. Okay, then you're, instead of having 4 times 3 times 3, which is 36 choices, okay, you would have 5 choices for your hats, because the 5th choice is to just not wear a hat. You'd have 4 choices for your shirts, because the 4th choice is to not wear a shirt. And you'd have 4 choices for your shoes, because the 4th choice is to wear no shoes. 5 times 4 is 20 times 4 is 80. You'd have 80 choices. But that's not quite the right answer. Let's go back and look at why. So we've come to the conclusion that I need to include an empty set for 1 centimeter. I need to include an empty set for 5 centimeters. And I need to include an empty set for 25 centimeters. So we saw just before how this actually becomes 5 times 4 times 4. Because this problem does allow for incomplete sets. You can just have, like I said before, a 1 and a 5 centimeter block. So that gives you 80 combinations. However, this little bit here is so tricky. It says how many different lengths of at least 1 centimeter can you make? Well, out of these 80 combinations, there is one of them that is literally just only empty sets. And an empty set is a set of no length. Therefore, it's not a set that includes 1 centimeter in it. Oh my gosh, my big moment. Mind blown. So the answer is 79, because you can't include that empty set. 79. So there's 79 combinations. I love this problem for so many reasons, but I think one of them is because it asks you to remember something you've been taught over and over, but to consider it even further. You know, maths is like an iceberg. You don't really know how deep it goes. You think you understand things. You think you know how the world works. And the more you learn, the more you realize, oh my gosh, I have no idea what's going on here. So, and that was my experience solving this problem a few years ago. It took me a long time to wrap my mind around how this worked. Yay! So much fun. Let's keep going. The next answer for the next Olympiad is 357. I'm not really going to go over this one. I don't think that was too tricky. Yeah, okay. This next one, I just use logic to solve it. Okay, and I'll kind of explain. Here's the answer. PR5T, so 6 is... What on earth? Go back. Undo. 6 is... Oh, my goodness. You cheeky program. Okay. 6 is P, 7 is R, 5 is itself, and 4 is T. Okay, so I need to take something, 6 away from something to make 8. So if I take 6 from 14, I get 8. How do I get 14? Well, I've borrowed next door, so this actually had become a 4. And what do I have to take from 4 to make 9? I need to take 5. Because if this was 5, then I had to borrow next door, and that became 14. Wait, hang on, that's not right. Oh, wait, no, that is right. Yeah, of course, 14 minus 5 is... Oh, I see, yeah, is 9. I was confused. Okay. And then, so that means that R was 7 before, and then when it borrowed, it became 6. And so then if I was trading next door, okay, 16 minus 7 is also 9. So if I swapped next door, this was 6, but now it's 5, and 5 minus 4 is 1. So I don't like this problem. Because I just find it really, really tricky to think about the state of things before and after you have to borrow. But it has helped me to talk it out loud. Anyways, that's how you solve it. Okay. 10 people stand in a line. The first one goes to the back of the line, and the next person sits down, so on and so forth. So that the person who was third is now the first person, right? Because the first one went to the back, second one sat down, so now the one in the front is the third person. Then that person goes to the back of the line, and the next one sits down, and it keeps going. Okay? So the question is, what was the original position in the line of the only remaining person? And it's the fifth. So the fifth person will be the last person. And if you don't believe me, we can do it over here quickly. Okay, here we go. So, first person number 1 comes over here, and 2 sits down. Okay, 3 comes over here, and 4 sits down. 5 comes over here, 5, and 6 sits down. 7 comes over here, and 8 sits down. 9 does the same thing, and 10 sits down. Okay, now just notice a little bit of a pattern here. What kind of numbers are these blue numbers? They're all the odd numbers. And what are the ones that had to sit down? All the even numbers. That should make sense to us just based on what's happening. The first one goes to the back, and the next one sits down. So we're eliminating all of the even numbers. Okay, so in this next context, if you think about it, what are the, quote, even numbers? What is every other number of the odd numbers? What are the new, quote, even numbers? Well, 1 will still survive, okay, because 1 is up next and it goes to the back. But 3 is a next number, so it acts like an even number. It goes away, okay? 5 survives. 7 doesn't. 9 remains. And 1 doesn't. 5 goes to the back. And 9 sits down. So you're left with just 5. Very cool problem. Tape 2 centimeters wide is used to completely cover a cube 10 centimeters on each edge. Find the length of the tape if needed in centimeters. You need 300 centimeters of tape for the answer here, or 3 meters. You can visualize it pretty simply. Okay, I've got a cube with 10 centimeters on the side. Okay, that means if the tape is, how wide is it? 2 centimeters? 2 centimeters. So then I've got 2 centimeter tape, 2, and then 2 centimeter tape, 2, and then 2 centimeter tape, 2, then 2 centimeter tape, and then 2 centimeter tape. So this is a length of 2. Another one is 4 total, 6 total, 8 total, 10 total. So I've covered that face. All right. How long is each of these? Well, they're each 10 centimeters because they're covering the whole length. So I've got 10 centimeters in length here, plus 10 centimeters in length here, plus 10 here, plus 10 here, plus 10 here. So I've got 50 centimeters per face. 50 cm per face. There are 6 faces on a cube, so 50 times 6 is 300 centimeters of tape. Oh, pretty straightforward. It's tricky if you can't visualize it, okay? So that's why drawing a picture for that is super helpful. This problem is, I think, really easy if you just assume that this person was born in the 1900s, okay? If you imagine this was like some random future problem and Dr. Bolton was born in the year 2800, well, you're going to be way off. Just assume that it's someone born in the 1900s and this becomes super simple. So the answer is 1926. I won't really go over it. Staircase, this is an easy problem. The answer is 50. Okay, that's how many more cubes you need to make this a 5 by 5 cube. The structure is already 5 by 5. So you got 5 here, 1, 2, 3, 4, 5. You got 5 here, 1, 2, 3, 4, 5, and you got 5 here. 1, 2, 3, 4, 5. So you're just trying to fill in, you're imagining these extend up and you're just trying to fill in the gaps. And you'll notice that the first gap that you can fill in, I thought about this like vertically, kind of like this, right? And then across 3, 4, 5, right? Sort of like slicing in a bunch of cubes. Oop, this way, to sit on top like this. Okay. And so that slice of cubes that kind of has to fit on top of that face to come flush with the top here, I know my drawing doesn't look amazing, would be a face of 5 times 4, because you've already got one of them taken up, right? I don't need 5 times 5. Then the next one would be 5 times 3, and then 5 times 2, and then 5 times 1. So 20, 15, 10, and 5. And you sum those together and you get 50. This is, I said it was easy in the beginning. Now that I'm talking it out, it's not. You really have to try to visualize this and hold a lot of information in your mind. It's good if you can build it. The next one is 19, and I quite liked this problem. If you don't believe me, we'll work it out over here really quickly. There are no descending numbers in the set of numbers from 100 to 200. Because if you think about it, 100 is not allowed. They've explained that here. You can't have a number with 2 digits that don't descend. So 100 is not allowed. And if 100 is the smallest number there, then clearly anything else is not going to descend. It's going to ascend. It's going to go up. 101 is an ascending number, so to speak. Okay, so none here. What about numbers start with a 2 in the front? Well, you could have 210. That's an ascending number. Could you have 211? No, not allowed. Okay, based on the rule here. What about 300? Okay. Well, you could have 310. Okay. You could have 3. I might just erase that. Sorry. You could have 320 and 321. For 400, you could have 410, 420, 421. And then you can actually go up and grab a 3 now because you've got a big number in the front. You got the 4 in the front. So 430, 431, 432. You're adding 3 each time now. And then the last set. So 510 would work. So would 520. So would 521. So would 530. 531. And then you can go up and grab the 4s. 430. 540. What did I just say? 541, 542, and then 543. All right. And if you sum all those up, you get those 19 numbers. Cool. All right. Last problem. Okay, one light flashes every 2 minutes. Another one flashes every 7 minutes. So here's my 2-minute light bulb. Here's my 7-minute light bulb. Okay. Just thinking about these as counting on. Okay, this one would flash like 2, 4, 6, 8, 10, 12, 14. Da, 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 da. The 7-minute one would flash on the 7th minute and on the 14th minute. So straight away, hopefully you can see that these will sync. They'll flash at the same time every 14 minutes. Now we know that they were synced at 1 p.m., which I'm going to write as 1300. Then they did their thing. At some point, the time became 3 p.m., which I'm going to write as 1500. And the question is, after this point here, when did they flash again for the first time? Okay, so really what we're asking is, how many groups of 14 will fit, how 14 minutes will fit between this time period? Okay, so I just have to figure out really how many groups of 14 will fit into 120. And if there's a more or less kind of remainder, then I can just calculate from there. So now 120 divided by 14 is a little bit of a kind of problem. So let's use a little bit of intuition here. What is 14 times 10? Well, it's 140. So that's too big. So I'm probably going to be multiplying 14 by a smaller number. And I can see right away, well, hang on. If I do 140 minus 14, I get 126. That's the same as saying 14 times 9. Okay, 126. So on the 126th minute, these lights will flash together. Okay, well, what is the 126th minute then? Well, if we started counting from 1 and we went 126 minutes later, well, 60 minutes gets us halfway to 2, and then another 60 minutes, 120 total, so 60 minutes, 120 minutes gets to 3, it's 120 minutes. So what is 6 minutes after 3? Well, the answer is 3:06 p.m. Yay! So I like this problem because it's deceptively simple to read, but you really have to think what's happening with these rates. You've got a 2-minute rate, a 7-minute rate, they sync up, then you have some period of time in which they're syncing and unsyncing, and then you kind of click the button and go, now, when's the next time it's going to happen? And they don't fit perfectly together. You get a bit of a remainder here, 126, 6 minutes over the 120 mark. Well, boys and girls, that's about an hour. I think I need to go get a big drink of water. My throat is killing me. Anyways, I hope you had fun with the work this week. I know I had fun giving it to you. Marking it was a blast. And I will see you on the internet.